So, good afternoon to all of you. Today we will discuss another thing in the transient analysis, and this is basically the step response of series RL circuit and step response of series RC circuit. Now, the question is how you can calculate the step response of series RL circuit. So, for calculating the step response of series RL circuit, we have a following circuit. Now, this is the circuit that we have, and in this circuit, we are using a step response, and after that, we are calculating that what is the current flowing through this circuit. If you see in this circuit is basically comprises of a voltage source Vs in series with a switch, in series with a resistance R, and also one inductor L. Now in this circuit the condition is already given to you, or from the switches condition you can see that at t is equal to 0 the switch is closed. So when t is equal to 0 the switch is closed, the circuit will becomes like this thing. And if you see this circuit, that is a voltage source, a switch is closed, we have a resistor R, we have inductor L. And since this circuit will be complete and this circuit will be closed, so accordingly what will happen in this case, we can apply the KVL. And when you apply the KVL in this circuit, you see you are got the first equation, and according to the first equation, that according to the you can say that the Kirchhoff voltage law, in a closed loop the sum of all the voltage drops in a load is equals to the source voltage. So you can say that when you apply the KVL in this circuit, it simply says that your source voltage is equals to load voltage. Now here the source voltage is equals to Vs and the load voltage is equals to VR plus VL. And since we know that the current flowing through the inductor is largely dependent upon the time, so we can take this current as I of t instead of I. The reason being, in case of resistor the current is not dependent upon time, but in case of inductor the current is dependent upon time. So that is why we are taking the current in terms of I of t instead of current I. So when we apply the KVL in the circuit, you can see that the KVL says source voltage is equals to load voltage. So based upon that thing, you have a source voltage is equals to Vs. You have a load voltage, and in this load you have two types of loads available. One is R, another is L. And in case of R, the voltage will be Ri of t, and in case of L, the voltage will be L di by dt. So I can write down that Vs is equals to Vs, Vr is equals to Ri of t, Vl is equals to L di by dt. And if you have all the three variables, we can substitute these three variables in equation number one. And when you substitute these variables in your equation number one, you can see that your supply voltage Vs is equals to Ri of t plus L di by dt, and we have this equation number two. So for calculating the value of I of t, what we have to do, we have to apply the Laplace transform. So I can apply the Laplace transform in equation number two. And when you apply the Laplace transform in equation number two, you can see that the source voltage, that is Vs, we having a Laplace is equals to Vs upon S. A resistor's Laplace, that is Ri of t, is having a value R into I of S. Whereas the derivative Laplace is basically equals to Si of S minus I0 negative, where this I0 negative is basically equal to current flowing through inductor at t is equal to 0 minus. And you all know that t is equal to 0 minus is basically called as initial condition. And you also know that at the time of initial condition, the inductor is replaced by short circuit, and we have to calculate the current flowing through the short circuit, or you can say that we have to calculate the current flowing through the inductor. One more important thing, that as you see at t is equal to 0 the switch is closed, but now at t is equal to 0 minus, that means at initial condition that switch remain open. So therefore at t is equal to 0 your circuit will become as look like this thing, that is a Vs, the switch will open, we have a resistor only, and the inductor will be replaced by short circuit, because it is the condition of the transient analysis that whenever you have to take the initial condition, and in the case of initial condition the inductor is replaced by short circuit. So when you replace inductor by short circuit, and you have to calculate the current through the short circuit. So here the current will equals to 0. The reason being we have an open circuit, and in case of an open circuit there is no current flow. So that is why your I naught will be equal to 0. And if you substitute this value I naught equal to 0 in your above equation, you are getting only the equation that is Vs upon S Ri of S plus Ls I of S. So here you have Vs upon S. I can take Is as common. So here we have R plus Ls into I of S. So from that equation, you can easily get the value of Is, and this Is will becomes as Vs upon L S into S plus R by L, and this is your equation number 3. Now, you see in your equation number 3, in a denominator, there are two factors. So we have to get a partial fraction. So I can apply the partial fraction of equation number 3. And when you see the partial fraction of I of S, that is Vs by L upon S into S plus R by L is equals to A by S plus B by S plus R by L. And when you go for the partial fraction by using substitution method, you can get A is equals to Vs by R and B is equals to minus Vs by R. I can substitute this A and B back to the equation. I of S is equals to Vs upon R upon S minus Vs upon R upon S plus R by L. So in order to get the current flowing through the circuit, we have to take I of t current, and we have given the I of S. So we have to convert this I of S into I of t, and for that thing we can use an inverse Laplace transform. See, a Laplace transform is basically converted the time domain equation into S domain equation, whereas inverse Laplace transform converting the equation from S domain, that is a frequency domain, into the time domain. Now here the current is given in S domain, that is a frequency domain, and we have to take the current in time domain. So that is why I have to take inverse Laplace transform, and when I take inverse Laplace transform, your I of t will becomes as Vs by R minus Vs by R e raised to power minus R by L into t. So this is the required equation, that is I of t is equals to Vs by R minus Vs by R e raised to power minus R by L raised t, is the current flowing through the step response of series RL circuit. So anybody having any doubt related to that particular topic, he or she can ask me. Otherwise, I will continue to the next topic. So anybody having any doubt? Yeah, anybody having any doubt?
No, sir.
It is understood to all. That is how we can calculate the value of step response of series RL circuit. Is everybody has understood? See, this is the derivation part and frequently asked in your university examination, that obtain the step response of series RL circuit, obtain the step response of series RC circuit. So this is one of the, you can say that, a derivation part of step response of series RL circuit. So I am again repeating you, anybody having any doubt related to that particular topic, that is how the step response of series RL circuit can be calculated? It is clear?
Yes, sir.
Can I proceed to the next topic, that is step response of series RC circuit?
Yes, sir.
Okay, fine. So based upon the same thing, you can see we have to calculate the step response of series RC circuit. Now, what will happen in case of series RC circuit? There is a slight change in the circuit. If you see a step response of series RL circuit, the circuit is a combination of R and L, that is resistor and inductor. But in case of step response of series RC circuit, the circuit has a slight change, and instead of inductor, we are using a capacitor C. So rest of the circuit remains same. In this circuit, we have a battery of Vs having a positive and a negative terminal, that is the DC supply. We have a switch, we have in series with the resistor R, and also we have a capacitor in series with R. Now again, the condition remains same, that at t is equal to 0, the switch is closed. It is given in the circuit diagram. You can see that arrow is towards downward, and we know that when a switch having arrow downwards, that means at t is equal to 0 the switch is closed. And also you know that in case of transient analysis, we have to analysis that at what happen at t is equal to 0. See, there are three things in transient analysis. Number one is t is equal to 0, t is equal to 0 minus, and t is equal to 0 plus. T is equal to 0 means the time of analysis, your time when you analyzes the circuit. T is equal to 0 minus means initial condition, what will happen before the t is equal to 0, and t is equal to 0 plus means what will happen after t is equal to 0. So there are three things to be occur in a transient analysis, that t is equal to 0, t is equal to 0 minus, and t is equal to 0 plus. So when we have to analysis the circuit, we have to analyze the circuit at t is equal to 0. So again, we have to analyze this circuit at t is equal to 0, and you see at t is equal to 0, the switch is closed. Now you see the switch is closed, the circuit will become as exactly same as in happen in series RL circuit. Here it is a circuit, you have Vs, switch is closed, R, C, circuit is complete, and when this circuit is complete, the current will start producing in the circuit. So you see again in this circuit that, just a minute. You see in this circuit that when you apply the KVL in the circuit, you have Vs is equals to VR plus Vc. Again, Vs is equal to Vs. Then you have VR is equals to Ri of t. Vc is equals to 1 upon C integral it dt. Because in case of capacitor, the voltage across capacitor is equals to 1 upon C integral it dt. I can substitute these values in the above equation. And when you substitute these values, you can see that Vs is equals to VR plus Vc. Vs is equals to Ri of t plus 1 upon C integral it dt. And this is your equation number 2. Now, in case of capacitor, we integrate the voltage across capacitor between the two limits. One is called as the initial limit and second is called as the final limit. Now, the initial limit is minus infinity to 0, and at that case, we have to calculate what is the voltage across capacitor at t is equal to 0 minus. So, the initial condition is what will happen before the switching at t is equal to 0 minus, what is the voltage across capacitor, and 0 to t is the final condition. So similarly, you can see that Vs is equals to Ri of t plus 1 upon C. We have Vc 0 negative plus 1 upon C integral 0 to t it dt, where Vc 0 negative is the voltage across capacitor at t is equal to 0 minus, and at t is equal to 0 minus, again you can see just like in case of inductor, the inductor is replaced by short circuit, whereas the capacitor is replaced by open circuit. So when inductor is replaced by short circuit, we have to calculate its current. That is, what is the current at the case of short circuit? And when capacitor is replaced by open circuit, we have to calculate what is the voltage across that open circuit, and or what will the voltage across that capacitor. So you can see here the voltage across capacitor is equal to 0. The reason being this switch will be open, and when this switch will be open, there is no current flow in the circuit. And when there is no current, there is no voltage. That means your initial voltage across capacitor is equal to 0. Okay, so when this voltage is equal to 0, we can substitute this initial voltage in this equation. So you are finally getting that Vc is equals to Ri of t plus 1 upon C integral it dt. Now I can substitute inverse Laplace transform, and when I substitute inverse Laplace transform, you can see Vs by S is equals to Ri of S plus 1 upon Cs I of S. Now here the differential's Laplace will be S into I of S, but in case of integral, the Laplace is Is upon S. So I can simply substitute the value of Laplace. I'm sorry, here it is Laplace transform. It is not inverse Laplace transform. You can take it on another, make it a correction that here apply the Laplace transform. Okay. So when I substitute these values, you can see your Is will becomes as VSC upon RC upon 1 plus RC. So again, this equation is in frequency domain or in S domain. And for calculation of your current in T domain, you have to take its inverse Laplace transform. And when I have to take its inverse Laplace transform, your will become equation becomes as I of t is equals to this value, that is Vs by R upon, you can see here, apply the inverse Laplace transform. So I of t will be equals to Vs upon R e raised to power minus 1 upon RC into t. So this is the required equation in time domain for a step response of series RC circuit. So what will happen in case of series RC circuit? The current flowing through the circuit is given by Vs by R, that is what is the voltage across the circuit, divided by the resistor into e raised to power 1 by RC into T. I hope you can understand both these derivations, that what is the step response of series RL circuit and what is the step response of series RC circuit. Now again, if anybody having any doubt, he or she can ask me. I'm waiting for your doubt. If anybody having any doubt? Yes, students, anybody having any doubt?
No, sir.
It is clear.
Sir.
So this is all about for today's lecture. I can share you. I will share this study material on your WhatsApp group. So kindly go through that study material and try to solve these both the derivation at your workplace. And if you find any problem related to that thing, you can ask me or you can message me. Okay. So this is all
Okay,
about
sir.
transient analysis